Hi everyone, my name is Brittany Burgess, and today I'm going to give a talk about stability, its relevance, how we determine the stability of a system, and then demonstrate stability using a code I created with Python. Before we dive into stability, I want to start off by talking about why stability is important and examples of the negative consequences that occur when stability fails. In 1940, the Tacoma Narrows Bridge was constructed, but as you can see from the photos, 4 short months later the bridge collapsed in a windstorm. The wind caused the bridge to start to oscillate, and because the system was unstable, the bridge began to move more and more until it eventually broke. This is a mechanical example that demonstrates why we need to know the stability of our system. On a biological note, biological systems are continually subject to change. So, if we had an unstable system, the smallest change could highly disrupt an entire process and prevent a cell from normally functioning. So, what is stability? Let's start with a simple example. An example of an unstable system is the ball on top of the hill. No matter which way the ball moves, it will never reach its original location back at the top of the hill. On the other hand, a stable system, the ball on the ground, will always roll back to its original location. Now, when looking at systems, we apply the same logic. As you can see in the diagram, when a perturbation is made in the stable system, the system relaxes back to the original steady state value. But when a perturbation is made in the unsteady state system, the system diverges away. There are also 2 types of stability, internal and external. Internal stability is changing the concentration, where external stability is changing the input. A system that is internally unstable will also be externally unstable. External stability can be determined using the same criteria used for internal stability. This transitions to our next topic. How do we actually calculate the stability of a system? One must first begin by creating a Jacobian matrix. This example up here in the left corner shows how you would get your Jacobian. The Jacobian is computed by differentiating the equations with respect to the steady state values. So as you can see up here, we have our 2 equations and we differentiate with respect to x1 and x2 for each function, and we get the following Jacobian. Once the Jacobian is created, the eigenvalues of the Jacobian must be calculated. This is done down here where I show how to take the determinant of the Jacobian matrix. For this specific example, we see that the eigenvalues are -2 and -4. All entries in the Jacobian are real, so we can have positive, negative, and complex eigenvalues as a result. In order for a system to be stable, all real components of the eigenvalues must be negative. This makes sense when looking at the solution to a 2-dimensional linear system of differential equations, as the exponents determine the decay and growth of the system. So inspection of the eigenvalues can tell us about the future behavior of the system. So here, the eigenvalues determine if we will grow or we will decay. Another method of calculating stability is using the transfer function, which is in the Laplace domain. The transfer function is a ratio of the output of a system to the input, and it describes the impulse response. Here's an example of a transfer function. The denominator of the transfer function is called the characteristic equation, shown here. The roots of the characteristic equation are called the poles, and they correspond to the eigenvalues in the solution to the homogeneous system. This means that similar to the Jacobian, we want negative poles in order to have a stable system. Now that we know how to calculate stability, we can use the eigenvalues to create various plots that demonstrate the stability of the system based on varying initial conditions. On the left is a chart that demonstrates the type of phase plot and the behavior we expect to see based on the eigenvalues produced from the Jacobian. On the right is a phase plot. This is a geometric representation of the trajectories of a system. Starting with different initial conditions, it tells us how the system will respond. Each axis represents one of the state variables. The first phase plot that we see is a stable spiral. As you can see, regardless of where you start, you are spiraled back to the center. This is representative of complex negative eigenvalues. The next plot is a saddle point. As you can see, in most locations you are unstable, but at very specific locations you're brought back to the center. This is representative of a positive and a negative real eigenvalue. The last phase plot is a stable system. As you can see, regardless of where you start, you're brought back to the center. This means that we have real negative eigenvalues. I will now transition to my code where we will apply the knowledge we just gained to a computational setting. As you can see, I have heavily commented my code so that it can be read and interpreted by any user. So, I will first briefly describe my code and then we'll run it. To begin with, I'm collecting the Jacobian matrix and initial input from the user. Once I received all the user values, I'm physically creating the Jacobian. By this I mean I'm taking the individual inputs and placing them into a matrix. I'm then printing that matrix to the user so they can verify it's the same as their Jacobian. Once I have the matrix created, I'm then getting the eigenvectors and eigenvalues of the matrix. I'm doing this by utilizing the built-in Python commands to get them. I'm then getting the real and imaginary components of the eigenvalues so that I can create an argand diagram. I'm doing this by plotting the real components versus the imaginary components. I then proceeded to create the time course diagram. As you will see on the left, this is the process that I performed on paper. I am then doing this computationally. As you can see, this is the solution that we're desiring to get. In order to be able to get the solution for x1 and x2, we need to solve for the constants. We do this by taking the inverse of the eigenvectors and multiplying them by the initial condition. So here in my code, I have my initial conditions that I'm putting into a matrix. I am then multiplying the inverse of the eigenvectors, which were previously determined in the code, times the initial condition to get the constants. I'm then determining a time range, which you could specify it to be whatever you want, but I just did 0 to 20 seconds. And then I'm making functions for x1 and x2 following this exact setup here. I am then plotting them over time to see how they change based on what the user input. I then created the phase plot by using the original Jacobian provided by the user to recreate the original equation. So here you'll see I'm doing the original values times x and y, which is representative of x1 and x2, and then I'm using the built-in streamplot function in order to create the phase diagram. Let's now run the code and see how it works. So, the first thing that pops up is an introduction, and then it asks for the first row and first column. So let's say we do -2, -2, 3, 1, and our initial condition is 1, 1. So the code runs. We see that the eigenvalues are both negative, real, and complex. So based off this, we'd expect a stable spiral. Moving this to the side, we see the graph that appears. Similar to what was expected, we have a stable spiral. So as we can see on the argand diagram, we have imaginary components and their negative real components. This is our phase plot, which is a stable spiral. So regardless of where we start, we're brought back to the center. When we look at a time course plot of x1, we see we started our initial condition, and over time we're brought back to the steady state value. And the same thing happens with x2. Let's run in another example and see what happens. So let's say this time we will do 2, 4, 3, 13, 1, and 2. This time we see that we have 2 positive eigenvalues. Based on this, we would expect to have an unstable system. When we look at the graph, we get exactly as expected. All areas are diverging away from the original center. As you can see from the time course plot, we're immediately shooting off to infinity, which is as expected because the system is unstable. We see that we have a positive eigenvalue as expected. There's only one here because of the range I set, but this could easily be modified. And let's do one last example. So in this example here, we will do -2, 0, -0.15, -2, -2, and 3. So based on these eigenvalues, we have -2 for both of them, so we expect this to be a stable system. When we look at the diagram, it's exactly as expected. So we have On our argand diagram, we have -2 for our real, no imaginary. We are brought back to the center on our phase plot because it's a stable system. And we started our initial condition at -2 and 3, and we go back down to our steady state. That's all I want to talk about today. Thank you for taking the time to watch my video.